Hey guys, moving on to another section today. Believe it or not, we are already on the 5th out of 6 sections of quadratics. This one's a longer section. It's probably the longest out of all 6. And to focus on how to solve a quadratic equation. So we're focusing on solving today. Before we go into actually solving by square roots, I just want to show you guys a quick little diagram. You should be getting a copy of this as well. Move that out of the way. And this just emphasizes the difference between vocabulary words that we used a lot when we did the absolute value unit. Also, when we were graphing, we used these vocabulary words. So I've been using x-intercepts, roots, zeros pretty interchangeably. However, there is a slight difference between each of them, even though conceptually they kind of refer to the same thing. And I think this little bubble above this girl's head kind of puts a really good summary to it. So she says, oh, so graphs have x-intercepts. So when we look at a graph and see where it crosses the x-axis, we're visually looking at x-intercepts. Equations have roots. So when we solved equations like x squared plus 5 equals 10, and we'll learn how to do that today. That's an equation. That'll have a root, and then when it's in function format, it has a 0. Function format would look like this. F of x equals x squared plus 16. And if I were to find the zeros of this, what number would you sub in for f of x? And the answer is 0. Okay, so when you actually are inputting 0 for f of x in order to figure out where it'll cross the x-axis and where the x-intercepts will be, then those are referred to as the zeros. Zeros and roots include imaginary solutions. So the two imaginaries. X-intercepts, we can't visually see imaginary x-intercepts on a graph, but algebraically, we can calculate the imaginary roots or zeros. So just a slight tweak in vocab, even though they're all referring to what the heck is x. They all mean find x, whether it's on the graph, solving an equation, or finding the zeros of a function in function form. Okay, so I just wanted to go over that before we actually solve. All right. So the goal today is to solve by the first of 3 methods, which is solving by square roots. So 5th section, section 2.5, solving quadratics. Okay, so we're trying to find the solutions. Find the roots, because technically the examples we're doing today are all going to be in equation format. So we're solving equations today. We're finding roots. If I threw an f of x in there, then we would be finding the zeros. So solving by square roots. That's one of 3 methods. The other methods that we're going to review during this section is solving by the quadratic formula. You would have learned that in Algebra 1. And then also solving by factoring. We've already learned how to factor, so that section won't really be anything new. We're just kind of combining skills that we've already learned together. Solving by square roots, there's 2 times when we use this strategy. So we're going to use if. The first case is if there is no b term present. So when you're analyzing your equation, if you notice that there is no bx term, so there might be an a term or a c term, or multiple a and c terms that haven't been combined, but there's no b term. That's when you can use the square root strategy. The other time we can use this is if the equation is in vertex form. Now I'm putting vertex form in quotations because technically it's not the exact setup of vertex form because it's not y equals. It won't be in function notation. But it'll be set up in a similar format where you can try to identify an a, an h, and a k value. There'll just usually be more than one k because the It's like terms haven't been combined. So vertex form is the other time we solve by square roots. The goal when we're solving by square roots is to isolate the factor that is being squared. So that's the first step, to isolate the factor that is squared. So look where the square is. And then square root both sides to get rid of the square. All right. And if it's in vertex form, there'll be an additional step after this because you'll have the H term that you need to move. But in the other format, you will be done. It's important that when you're solving by square roots, that we have to remember the plus or minus sign. Or you will only end up with one root when there's supposed to be two roots. Okay, so you really should be getting two solutions for all of these examples. Two solutions. They might be two real solutions. Okay, visually we would be able to see two x-intercepts. It might be two imaginary solutions. So visually we wouldn't be able to see any x-intercepts. And then the third case, which will come up more later in the year, but I'm going to mention it right now, is when we get just one solution, but that solution is technically called a repeated root. So it counts twice. So all quadratics, sorry, I was going to sneeze. Okay, anyway, all quadratics really should be having two solutions, either two real, two imaginary, or if you get one, it's known as a repeated solution. And that's when the vertex is on the x-axis. That solution actually counts twice. All right. I guess if you want a little side note, I wouldn't write this down, but for example, if you had something like x plus 2 squared equals 0, I don't know why that calibration is so off right now, and I solved that using the method we're about to use. When you square root 0, can you have a positive and a negative 0? No, you can't. You do just have 0. So you'd only get one solution here, but that solution actually counts 2 times, because if you think of writing x plus 2 squared as x plus 2 times x plus 2, and you found the x-intercepts of that, like we did in the graphing section, the negative 2 x-intercept would count twice. Okay, you'd get the negative 2 here and negative 2 here. That's what I mean by repeated solution. But that'll more so come up later in the year rather than right now. All right, let's get to it then. The best way to learn how to do this is to just actually do it. Make that go away. Sorry, I had to pause. My headphones fell off earlier. And now all of a sudden my calibration is off. Let me go ahead and redo that. Hit pause. I hear all this dinging right now. Go away. All right, back on track. So let's solve. Let's find x. Let's find the roots. Let's find our solutions. And we have a total of 6 examples we're going to do today. Here's the first one. 2x squared minus 5 equals 27. This can be solved by square roots because if you analyze the equation, you'll see that there's no b term present. This is an a term, a c term, and another c term. No bx term is there. So goal, isolate the factor that's being squared. So we have to isolate this x squared. We'll move over the 5. Let's add that over. It's just solving like a typical 2-step equation. And then you would divide by 2. Some people are square root happy and try to square root way too soon. Okay, you gotta get rid of that coefficient first. And you'll get x squared equals 16. And then you can square root both sides. And what do you need to remember? Yes, your plus or minus sign. So we get plus or minus 4. So we have 2 roots there, positive 4 and negative 4. Okay. Well, let's try another one. So 5x squared minus 4 equals 6x squared plus 21. Looking at the equation, there's still no b term present. We have a terms and c terms, but no bx term. And when you have more than one a term, your goal for this is to first move the a terms to the same side. You don't need to move everything on one side. Notice in example 1, we never set it equal to 0 there. Your goal is to isolate x. So you don't want to move everything in number 2. Start off just by moving the x squared to the same side. I'm going to move the smaller one to avoid some negatives. So I'm going to subtract the 5x squared, which will leave you with negative 4 equals 1x squared plus 21. And from here, I would say pause it, see if you guys can finish it on your own. I'm going to keep going, and you can check. I'm going to subtract the 21. That'll give me negative 25 equals x squared. I can square root to get rid of the square, using those are inverse operations. And I will get x equals, still my plus or minus sign, but I have a negative under the radical. That means my answers are imaginary. So the square root of 25 is 5, and the negative means it's an imaginary solution. So we get positive 5i and negative 5i. Still 2 answers, 2 imaginary answers, 2 imaginary roots on that example. Okay. This one, also pause and try it on your own. 3x squared plus 10 equals negative 26. Go for it. See if you can solve for x. I'm going to keep going. Subtract the 10 from both sides. Divide all your terms by 3. And square root. 12 is not a perfect square, unlike in number 2 where 25 was a perfect square. So we're going to use our simplifying strategies. We can break 12 apart. Ooh, calibration really off again, even though I just did it. I'm going to get x equals, I'm going to break the 4, or the 12 into radical 4 times radical 3. The negative still comes out as I. And then it can get a little confusing on the order you write that in. Plus or minus still is out front, because you plus or minus, then your answer. And the order we wrote this in, based on the section we did yesterday and the day before, would be 2i radical 3. Because the square root of 4 becomes 2, the I should go in front of the radical, and then the 3 stays inside. All right, so that's 3. All 3 of those were in standard form, but we're missing a b term. I'm going to throw one more at you that's going to involve a little more fractions, and then we'll talk about the equations that will be in the vertex format. So 3 minus 5x squared equals negative 9. Pause the video, try it on your own, see if you can understand it. I'm going to check with my work. I'm going to subtract the 3 to the other side. Watch your signs. And divide by negative 5. Now 12/5, I can't simplify that at all. The 2 negatives will change to a positive, but I can't, there's no common factor between 12 and 5. When I square root both sides, I can square root them individually, which will then allow me to see that I'm going to have to rationalize the denominator. So I'm going to multiply the top and the bottom by radical 5. I'll get x equals plus or minus. The 12 and 5 are both underneath a radical, so I can multiply them to get radical 60. Square root of 5 times square root of 5 is the square root of 25, which is just 5. I cannot divide 60 and 5, but I can attempt to break apart 60 into 2 other radicals. And if you find the largest perfect square that goes into 60, you're going to figure out that that's going to be 4, and it goes into 60 15 times. So my final answer will be plus or minus. The square root of 4 is 2. The radical 15 is going to stay inside, and then it's all over 5. Double check the parts that aren't under a radical, the 2/5, but 2/5 you can't do anything further to simplify that. So that's pretty much all there is to it. in terms of solving by square roots when there's no b term. Let's look at a couple of examples then that are in the vertex format. So fifth example, 3 times parentheses x minus 2 squared equals 21. Goal is still the same. Isolate whatever is being squared. So in this case, our goal is to isolate this x minus 2 quantity because that's what's being squared. We'll do that by dividing both sides by 3, leaving us with x minus 2 squared equals 7. I can't distribute the 2 because of the minus sign, and I don't want to FOIL this out. I don't want to do x minus 2 times x minus 2 because then I'll have a b term, and if I have a b term, I can't solve by square roots. So I can get rid of that square right now by square rooting that whole quantity. Woo, crazy square root box. So I square root both sides. On the left, the square and the square root cancel, leaving you with x minus 2. And on the right, the 7 can't come out of the radical because 7 is not a perfect square, so I just write plus or minus radical 7. Notice I put the plus or minus now, not on the end, not at the end. The plus or minus belongs as soon as you square root both sides. So as soon as I square root both sides, that's when I put the plus or minus. Don't wait till the end or your answer will be wrong. I'm going to add over the 2 to finish isolating the x. And when I add the 2 to the right-hand side, 2 and radical 7 are considered not like terms. So I can't combine them. I write the whole 2 first, and then plus or minus radical 7. You can leave it in that radical notation. If I wanted a number that maybe made a little more sense to me, if I wanted to add those or subtract them, I would have to change radical 7 to a decimal. So on the calculator, take the square root of 7, and then I could do 2 plus that decimal and get one answer, and then 2 minus that decimal and get my other answer to get my 2 roots. Okay? These are real solutions. Even though it's under a radical, these are not imaginary. There's no I anywhere. This would still be 2 real solutions. All right, last question for the day. You guys have 2 nights on this homework assignment, but you can definitely start it tonight. So last example is 3/2 times x minus 2 squared minus 8 equals 16. Still follows that vertex form. Okay, like this is my A, my H, my K, and this is like another K term over here. When isolating the square on this problem, I'm going to move the 8 first, so we're going to add over the 8. And then how do we get rid of a fraction as a coefficient? So last example we divided, but we don't divide by fractions. Think about that for a second. And yes, ding, 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 the answer is to multiply by the reciprocal instead of dividing by a fraction. So we now have x minus 2 squared equals, on the right, this would have become 48 over 3, which is 16. Square root both sides, and x minus 2 equals, nice job. Hopefully you said plus or minus 4 and not just 4. I'm going to add the 2 over, and this time I can combine. In the last example, I could not combine, if we look up real quick and you look at your notes, I could not combine the 2 with the radical 7 because 7 was underneath the radical. So I kept them separate. Unlike in this example, I can combine these because the 4 is not under a radical. So what you're essentially doing off to the side, and you don't have to write the steps, I want to show you where my answers are going to come from. You're doing positive 2 plus 4, and you're doing positive 2 minus 4. It's the 4 that's positive or negative, not the 2. So positive 2 plus 4, positive 2 minus 4. Or you could read it the other way. You could do positive 4 plus 2 and negative 4 plus 2. Either way, you'll get the same answers. If you do positive 4 plus 2, you're going to get 6. And if you do negative 4 plus 2, you will get negative 2. So there are the two solutions. If you forget that plus or minus sign, though, with the 4, you're only going to end up with one solution when there should have been 2. So plus or minuses, you need to remember it. So I'm going to end there for today. Tomorrow we're going to do a couple more examples and some real-world practice. So we're going to solve some real-world problems that involve square rooting. Let me stop.